Swayam Prabha. Digital India. Educated India.
I would like to, this is an unplanned hour, but what I'd like to do is to finish up some loose ends from last time and then get to a physical topic with some physics rather than math. And based on what Professor Ghanshyam Date told you this morning, I would like to do some relativistic physics, tell you something about special relativity with special focus on what it implies for physical particles. This is something which is useful, which will be useful to all of you, various stages. So let's first finish off this probability game that we were playing about capture by the tiger. So let me show you how this problem is done and why it's a fairly difficult problem, but it's done by a very simple trick. And the trick was the following. You had an infinite lattice over the negative integers, -1, -2, etc. And then there was a starting point 0 here, and there was a tiger or a crocodile in site 1. We wanted to ask for the probability that you escape the tiger, because there's an infinite amount of space here. The problem should be done in its generality by saying that the probability of a jump to the right from any side to any other side is P, and the probability of a jump to the left is Q, which is 1 minus P. We will solve this for general P, and that will then tell us what the situation is for P equal to half, which is an unbiased coin. Okay. Now let me use some notation. Let me call C of P equal to the total probability of capture. In other words, captured by the tiger or crocodile at site 1. That's the total probability of capture starting at 0. Capture at 1 starting at site 0. Okay. We can write down a formula for C of P in the following way, but it's hard to calculate a priori because C of P has a contribution where you start at 0 and jump with probability P to 1 right away. You're captured. But you could also have gone to -1, come back to 0 and then come here. Or you go to -2, jump back and forth between -1, -2 any number of times, come to here, come here, etc. So you can see there's an infinite number of random walks that you have to average over, that you have to sum over. Any number of intricacies are possible. Way down here you could be jumping back and forth forever, and then you come back here finally. So the question is, what is the C of P? And the way you go about it is like this. C of P is equal to, first, the probability of capture in one step. That's the first process. From 0 you jump with probability little p to 1 and you're finished. So certainly this is a contribution term plus all the rest, all the other random walks. But those would involve a first step where from 0 you go to -1, and the probability of that is Q. And then now you're at -1. And this is a Markov process. The past is forgotten. It's forgotten as to how you got here. All that is taken into account there. From -1, how are you going to be captured? From -1 you first have to go for the first time to 0. And from 0 you have to go to +1. The probability of going from -1 to 0, the total probability, is the same as the total probability of going from 0 to 1. Why is that? Suppose for a minute you had a barrier here at L, -L. Would that same statement be true or false? It would be false. Because you have an infinite possibility here, infinite lattice here, it seems translationally invariant. It doesn't matter whether you want to go from -1 to 0 or from 0 to 1. The probability is the same because you have an infinite amount of space to the left. But if you had a barrier here, the point -1 is on a different status from the point 0. Because the point -1 is L -1 away from this, but this is distance L away from this barrier. So the fact that you have an infinite lattice to the left is very crucial that this process is translationally invariant. The probability of going from here to here, the total probability is the same as that of going from here to here. Okay. But the probability of starting at -1 and going to 0 is C of P. And now you are back at 0 and you want the probability of going from 0 to 1, which is C of P. So you get an equation which is this. Now you have taken all possibilities into account. There is no other possibility. Now if you ask me to write down the C of P explicitly in terms of P's and Q's, that's going to be very intricate. But I don't need it. Okay. I have this quadratic equation for C of P. And let's solve it and see what happens. So you have QC squared minus C plus P equal to 0. That's a quadratic equation that even I can solve. It's very easy. So this implies that C of P is equal to 1 plus or minus square root of 1 So that's your total captured probability. But there are two routes and you have to choose the route that is physically relevant here. We will see how to do that in a second. So C of P is equal to 1 plus or minus square root of, and what's inside the bracket? Q is 1 minus P, so this is 1 minus 4P plus 4P squared. That's a perfect square, right? What happens next? What should I write? I want the square root of 1 minus 2p whole squared. What is the square root of 1 minus 2p the whole squared? Can it be negative? Cannot be negative. What's the square root of 1 minus 2p the whole squared? Absolute value of 1 minus 2p. Mod 1 minus 2p. You want positive square root. The plus or minus already takes care of the possibility that the square root has both signs. So this is mod 1 minus 2p. That's very crucial. Q is 1 minus P, by the way.
Sir?
Pardon me? The square root of this square, suppose I had log of this guy, what would you write?
Because Q is 1 minus P.
Yeah?
So we'll get P, 4P square minus 4P plus 1. So we'll get 2P minus 1 instead of 1 minus
1 minus 2p the whole squared is the same as 2p minus 1 the whole squared. Do you object to that? Okay. I like to write it as 1 minus 2. Okay.
How can we write 1 minus 4pq as 1 minus 2p the whole square?
Come on, come on. It's a perfect square. Yes? Look, you have to correct me if I'm wrong. Is it right or wrong? Right? It's that bewitching hour in the afternoon when you feel sleepy, yeah? 1 minus what? 5p.
Yes.
What is this quantity? I'm starting to... What is this quantity? 2x minus 1 the whole squared. I mean, why 5p? There's no bonus here. Okay? Agreed. But we got to decide which root is relevant to us. If p were equal to 1, what would happen?
Sir, is q 1 minus p?
What?
1 minus 4p into 1 minus p will not give me 1 minus 4p plus 4p square. It will give me 1 minus 5p plus 4p square.
What am I missing here? What am I missing here? Is it right or wrong? It's okay. I had a chemistry teacher in college who was somewhere in Delhi, who was fresh out of his degree from South India. He came over to Delhi and he was a teacher in the department and he was teaching chemistry. And he told us all about sugars and so on, and he said what fructose was, what lactose was, etc., etc. And then, after he finished his explanation for about an hour, one of my friend's classmates got up and asked, he said, "Is glucose a sugar?" So the gentleman was completely taken aback. And then he came out with a reply which I still remember. He said, he had a very strong South Indian accent, and he said, "See," you could see he was trying to control himself, but he finally just said, "See, after listening to the Ramayana for the whole night, the fellow asked whether Sita was Rama's uncle." And then he says, "Your question is like that." And then he went back to the blackboard and he explained lactose again, and he turned back and said, "I correct myself. Your question is worse than that." I'm not saying that here, but no allegations. So is this okay? Are we on the right track? Okay. Now, if you put p equal to 1, what is C of 1? Yeah, I'm going to do that slowly, we'll see. But what is C of 1?
1 plus or minus?
No, suppose you're definite to jump always to the right, then what's the probability of capture? 1. It's definitely 1, right? So C of 1 is equal to 1. And what is C of 0? If you never jump to the right, the probability of capture is 0, right? C of 0 is 0. This corresponds to Q equal to 1. So put P equal to 0 and see what happens in this. You get 1 plus 1 for the positive root divided by twice 1, which is 1, right? If you put P equal to 0. Whereas C of 0 should be 0. So what should be the root? 1 minus. So this is the correct root. 1 minus. The plus root is not physically significant. It doesn't have the right boundary condition. So we have our answer so far, which is the probability of capture. Why it's what? Because I want the condition that if you never jump to the right, the capture probability is 0. And never jump to the right means P is 0 and Q is 1. So C of 0 must be 0. But if you put p equal to 0, the plus root does not give you 0, the minus root gives you 0. Right? So C of p is 1 minus this guy. Definitely. Now we have two cases. Because you have a modulus sign there, we have two possible cases. So case 1, p less than half. If p is less than half, is 1 minus 2p positive or negative? P is less than half. 1 minus 2p is positive. So the modulus is just 1 minus 2p. P over 1 minus p. Because mod 1 minus 2p becomes just 1 minus 2p. What if p is bigger than half? One minus, instead of mod 1 minus 2p, I should now write 2p minus 1 because it's p is greater than half. So it's 1 minus 2p, the 1 adds up, it's 2 minus 2p, that's twice 1 minus p, twice 1 minus p. It's a constant. We are ready to draw a picture now. So it's come out to be something very non-trivial. So C of p has this picture now. Here's little p, this is the point 1, this is the point 0, this is C of p. And in the same scale, this is 1. For p greater than half, C of p is just equal to 1, just a constant. And what happens for p small less than half? It's p over 1 minus p. What happens if p is very close to 0 but positive? This 1 over 1 minus p, we can neglect the p compared to 1 because it's very close to 0. And the answer is roughly linear, p. So it starts off like this and then goes and touches that. But we don't know whether it's going to do it like this or like this, but the slope here is 1. 1 minus p. What's the slope at this point at half? First of all, is the probability of capture even continuous? We have to check that first. We know that for p greater than half, it's 1. For p less than half, it's p over 1 minus p. What happens at p equal to half? It becomes 1. So it says if you have an unbiased coin, you're definitely going to be captured still, because we are not sure of that case at all. At least physically, intuitively, you would say if the probability of a jump to the right is greater than half, he is definitely going to be captured. If it's to the left, may or may not be captured. But here, you're for sure at half, you're going to be captured. So it joins at this point, but the question is it going to join like this or like that? What's the slope at a half? You need the derivative, formula for the derivative of a ratio of two functions, right? C of p is p over 1 minus p. C prime of p is equal to 1 over 1 minus p minus p times the derivative of this guy here, minus because it's in the denominator, so there's a 1 minus p the whole squared, and then there's a minus p differentiated, so that's plus. So this is going to give you a 2 on top, this is going to give you another 2 on top. So the slope is 4. It's steeper than the 45-degree line. We are therefore guaranteed that this guy is going to go like this. And hit it like that with slope 4. The slope here is 4, the slope here is 1. That's what this graph looks like. This is the probability of capture. What's the probability of escape? 1 minus this. So I leave you to picture 1 minus. This will become a 0, this will go up and flip over. So at p equal to half, which is a fair coin, the entire system changes behavior from something where capture was not certain, the capture had a probability less than 1, to a region where the probability is 1, and it remains 1 for all larger p. Okay. So this is how problems in probability are solved, but you have to look at all these cases very carefully. You can also ask the next question, and this we won't answer here. How long on the average does it take to be captured? Assuming that capture is a certain event, in other words, the probability is 1, p greater than or equal to half. The question is, what's the mean time for capture? Well, you can guess what the answer is as p approaches 1. If p is exactly equal to 1, the very first shot you are captured, so the time taken is just 1 unit. If p is half, you still got probability of capture equal to 1, but it turns out that in this case, the mean time to capture starts at 1 at this point and is finite for all values of p greater than half, but at p equal to half it becomes infinite. So we have a process that is sure to happen rigorously, but takes an infinite amount of time on the average to happen. So it's called a null recurrent process, but that's a thing in probability theory, we won't talk about that. Okay. So you have to be careful when you make probabilistic arguments, because it can be quite subtle. Okay, what shall we talk about now? Special relativity. Yeah, what Ghanshyam was trying to say in the morning, let me say it in a slightly different way, from the point of view of the postulates of relativity itself. So very quickly, special relativity is based on two premises. One, there's a principle, and two, there's a postulate. A principle is a very general one. It was known to Newton actually, it was known to Galileo, although he didn't know it in this language. And that was the concept that if you have two frames of reference, two observers with coordinate frames, which are related to each other by one is by a rotation in space, the three axes are oriented differently, and the other is one of them is moving uniformly with respect to the other, it's called an inertial frame, then the laws of physics are the same in form in both frames. What laws of physics is not specified, they are the same in form. That is Newtonian relativity or Newtonian Galilean relativity, and that continues to remain true in Einsteinian relativity. But the second part of it, the postulate, puts in some physics. There is no physics here, it is just a general statement that the laws of nature are the same in form, and I will explain what the significance of that is. But the second one has some physical input into it, which I will state in a minute. Okay. First, let us come to this laws of physics being the same in form. All of you studied Newton's laws of motion, and you have learned this thing that the force is the mass times acceleration, okay, for a physical body of mass m. And this F has this arrow put on it and A has an arrow put on it. What is the meaning of that arrow? What is the vector quantity? Direction with respect to what? Who gives you this access? You can't decide the laws of physics arbitrarily. It's not a legal framework or anything. Can't be arbitrary. How do you know you're right? Who gives you this access? There's something very deep here which I want you all to understand at a gut level. It takes a little bit of thinking about it, but you have to understand it. Who gives you this access? Experimentally verified is just a convenient way of saying that you don't know. Put the blame on the experiment. How did you get experimentally verified? First of all, you read this book, and your books say this, right? Do they also specify the axes with respect to which you are finding the vectors components? In the same book, on the same page, have they also drawn a picture of a coordinate axis and said, with respect to these axes? Do you believe that the same book is being read in Timbuktu? Yes? It's being read all over the world. Their axes are definitely different from yours. So how do you know that it's right in their axis and not in your, and not just in yours? How do you know this? That's not true. I measure the force, I measure the velocity of a particle, say. Both measured in the same, with respect to the same axis. I agree. But I come and do the following. Forget force even, I look at the velocity of a particle. I measure its velocity and I discover it's got components Vx, Vy, Vx equal to 1, Vy equal to 6, Vz equal to 3. I discover in some units meters per second, I discover the velocity of the particle is this. I go and sit on top of the particle. It's not moving with respect to me. The rest of the universe is moving past it, right? In that frame of reference, let me call it by prime. I get 0. There's no velocity at all. The components are 0, right? Relative to my frame of reference, surely, with respect to. So in two different frames, the velocity is numerically different. So it's not even invariant. What's meant by this law then? The values of the components will depend on the frame. What's the use of such a description? All right, I'll take a class of all inertial frames moving uniformly with respect to each other. The numerical values of any vector are going to depend on where your origin of coordinates is and what frame you're in. But it's never specified. So what's the meaning of this law? What does it really mean? Yeah, it's saying a lot of things. When we ask students what's the meaning of this law, what's the physical interpretation of this law, they tell you force is mass times acceleration. Is that a good answer? If you write F equal to ma, they say, oh, that's all mathematics. But you ask what's the physical law say, then you say force is mass times acceleration. That's just reading out the symbols in words. It's not explaining this. This is telling me a lot of things. It's telling me, we'll come to this in a minute, it's telling me that F is a vector, A is a vector, M is a scalar. In other words, it doesn't change under rotations, but the vectors will change components under rotations of the coordinate axis. It tells me the vector of A is directed along the vector F. It's telling me a lot more. It's telling me whole books. It's telling me all of Newtonian mechanics. Because it tells me also what is very special about this. What would you call, I call it a response, stimulus-response relationship. There is a stimulus acting on the particle and the particle responds with some response. What's the stimulus here? And what's the response of the particle? Acceleration. And that's proportional to m, so the response is proportional to 1 over m times the force. What is so special about this law? What's the form of this law is something very, very special. What does it tell you? Let me put it in another way. If I apply a force F1 and I get an acceleration A1 and I apply a force F2 and the acceleration is guaranteed to be A2 in this case, what does it say if I apply the force F1 plus F2? Vectorial addition of A1 and A2. What's that called? you are guaranteed that if I apply a force F equal to F1 plus F2, this will produce an acceleration A, where A is guaranteed to be A1 plus A2. How is that magic possible? What is this? It's magical almost. Why is that possible? Because what property of the equation is making this possible? If I superpose these two forces, the accelerations get superposed. So the response is a superposition of the individual responses to the individual forces. What sort of equation will have that property? Suppose the response acceleration had been proportional to the exponential of the force. Would that still be possible? Linear. Linear. It's a linear equation. It makes superposition possible. Otherwise, the whole thing is gone. Suppose the force had the acceleration depended on the square of the force, then you're finished. The linearity is what is responsible for the superposition to be valid. So it's telling me that. It's telling me a lot of other things too. Now let's come back to ask, what exactly is meant by a vector? What is the meaning of writing this equation in textbooks? And what's the purpose behind their not telling you with respect to what axis? Yeah, exactly. They're not telling you with respect to which coordinate system because it doesn't matter. It's true in every coordinate system which is inertial with respect to the original one. So if you're guaranteed that in your frame of reference, if you discover that the particle has an acceleration A when you apply a force F, then another observer who applies a force F prime is guaranteed to have an acceleration A prime, where A prime is related to A in the same way that F is related to F prime. It has the same transformation law. When you want to make laws form invariant for different observers, you should write the laws in terms of quantities which carry their own dictionary of transcription from one frame to another. So the right way to define a vector is not that it has a quantity with magnitude and direction, because the first question you should ask is direction with respect to what? And then you are told with respect to this coordinate system, but it's also true for other coordinate systems, right? So now tell me, how would you define a vector? I'll repeat my statement again in technical terms. When you want certain laws to be invariant in form, certainly this is invariant in form. It is not invariant in numerical value, because A and A prime will have different numerical values and F and F prime will have different numerical values. We don't care. But the form of the equation is the same in both frames. When you want the form of an equation to be the same under certain transformations, you must express that equation or law in terms of quantities whose transformation properties are known to you already.
Sir, anything which follows vector law of addition is right.
So now tell me what a vector would be. You have to now immediately ask me with respect to what transformations. And the conventional vectors you are used to are in Euclidean space in 3 dimensions or in 2 or in 1, whatever. And the transformations are rotations of the coordinate axis. So a vector in your definition, the elementary definition that you are talking about, is a set of 3 quantities, 3 real quantities. They form together a vector, a triple, which transforms under rotations of the coordinate axis in the same way that the coordinates themselves transform. So if you tell me how the coordinates x, y, z become x prime, y prime, z prime, any vector is a quantity which also, set of 3 quantities which has the same transformation law. That's my definition of a vector. Let me do this in 2 dimensions and show you. You're already familiar with this. So let me do it in 2 and show you what a real vector is. A vector is in 2 dimensions.
So should the transformation be linear for it to be?
Yeah, that's the next question. Should the transformation be linear? You can therefore have vectors, scalars, tensors, etc., and more general quantities under all kinds of coordinate transformations, under rotations, under translations, under rotations and translations, under Lorentz transformations, under special relativity transformations, under general relativistic transformations, etc. They are tensors in the general case, etc. So you always have to specify the group of rotation of transformations. It's not specified in elementary textbooks, but what is understood is that it's rotations of the coordinate axes. And let's do it in 2 dimensions. All it needs is a little bit of trigonometry. So I have a plane, 2 coordinates x and y, and I rotate the coordinate axes by some angle alpha, and this is x prime, and this is y prime. Can you write down x prime and y prime in terms of x and y? Yeah, there is a trigonometric formula here which depends on alpha. Okay. That's how the new coordinates are related to the old coordinates. There is one point which is left unchanged, the origin. So we are talking about rotations about the origin, and in a plane there is no third dimension, there is only x and y. So the rotation is about a point. You are used to understanding rotations about an axis. I will prove to you that you don't need that at all. You don't need that at all. It's just rotation about the origin O. How do you know the origin is left unchanged? You put x and y equal to 0 and you get x prime y prime equal to 0. What property of this equation in this set of equations makes that possible?
Linear.
No. If A1 and A2 are constants, that is still a linear equation.
The factor is doesn't have a constant.
Doesn't have a constant. There is a technical term for it. What kind of equation doesn't have a right hand side which is non-zero? Homogeneous. Who said homogeneous? Very good. Homogeneous equations. The moment you make it A1 and A2 here, the equations become inhomogeneous. Okay? So homogeneous equations. The origin is left unchanged. They are linear homogeneous equations, okay, leaving a point unchanged. What other property that can we speak or think of under this rotation? If I have an arbitrary point here, the distance from the origin is given by the Pythagoras theorem, square root of x squared plus y squared there. What's the distance from the origin in the new frame? It's x prime squared plus y prime squared. Does the distance from the origin change under a rotation? Does the distance between any 2 points change under a rotation? Doesn't change. So that's another property. The distance shouldn't change. What else is preserved? Is this a right-handed coordinate system or a left-handed coordinate system? It's a right-handed coordinate system. Does the new coordinate system, is it right or left-handed? Right. There's no reflection. For instance, if I had this x, y, and I had new frame x prime, y prime, that's a left-handed coordinate system because I have reflected about this y. It's not a rotation. You can't obtain it by a rotation. Okay? So the orientation is preserved of the axis, the handedness is preserved, the distance between 2 points is preserved. What else is preserved? Is an area element preserved or not? If I have a small area element here, is the value of this area element changed under a rotation? No. So the orientation is preserved, area is also preserved. In 3 dimensions, volume would be preserved. Okay? So rotation has all these properties and they are all encapsulated by doing the following, by writing one below the other and writing this as a 2 by 2 matrix. What sort of matrix do you call this? It's a column vector, right? And what kind of matrix is it? N by n or 2 by 2 or 3 by 3 or what is it? It's a 2 by 1. And what about this guy? 2 by 1. What about this fellow? 2 by 2. And then this cancels out and gives you a 2 by 1. Is everyone familiar with matrix multiplication?
Yes.
Good. So this is the matrix. It's called a rotation matrix because it's got a very special form. Okay. What's the determinant of this matrix?
Cos square of 1.
The determinant is 1, right? What property, geometrical property does the determinant 1 imply here? The area is unchanged because dx dy is the same as dx prime dy prime. Scales are not changed at all. What other property do you know of this matrix? Let me give it a name. Let me call it R of alpha. It's a rotation matrix parameterized by the angle alpha. If I go like this from x prime xy to x prime y prime by rotating, I can undo the rotation by going in the opposite direction. No. Yeah, so physically if I rotate by minus alpha, I go back to the original coordinate system, that's the inverse transformation, right? So it will turn out that R inverse of alpha must be equal to R of minus alpha. But what is R of minus alpha equal to? Just look at this. If I put alpha to minus alpha, what do I get? I get cos alpha here remains unchanged, but this becomes plus sine alpha, this becomes minus sine alpha. It's the transpose. So we've just proved the property that R inverse alpha, R inverse for any alpha is equal to R transpose. But R inverse is 1. So it's telling you that the identity matrix. The matrix's inverse is equal to its transpose. What do you call a matrix whose inverse is equal to its transpose? Yeah, what's it? Ortho? Orthonormal? Orthogonal, yeah, it's an orthogonal matrix, right? So every rotation is an orthogonal matrix. What property of this rotation does that reflect? It's not immediately apparent from here, but the fact that the distance between 2 points is unchanged is guaranteed by the fact that it's an orthogonal matrix in any number of dimensions. So now tell me, what's the definition of a rotation of the coordinate axis? It's a linear transformation, it's a homogeneous transformation, it preserves orientation, orientation preserving, orthogonal, some of these properties follow from other properties, but these are basic properties, and it's got unit determinant, unimodular. All these properties are needed. If the determinant is -1, it is still a rotation, but it's called an improper rotation, because it's made up of a proper rotation, which is determinant +1, multiplied by something like a reflection. But you got to be careful about the dimensionality of the space you are in. For instance, if you are in a plane as you are now, and I have a coordinate axis like this, x and y, if I do a parity transformation, if I change x to -x, y to -y, then I get this transformation. That's called parity. All I've done is to take a vector r and replace it by -r. I've changed the signs of all the components of this vector. Okay. Is that a proper transformation or an improper transformation? Written as a matrix, how would that look? If I say x prime is -x, y prime is -y, what's the matrix that I have? -1, 0, 0, -1. Right? That flips all the axes and doesn't do anything else. It would look like an improper transformation, but is it or is it not? What's the determinant of that? +1. So it's a proper transformation. How do you explain that? Determinant is 1, but then I've reflected about both axes. Area will be the same whether the determinant is +1 or -1. The orientations will not be.
The relative relation between x and y.
No, it's much simpler than that. You can get this from this by just rotating by 180 degrees. Just rotate the entire coordinate system by 180 degrees by pi, and you're. Can you do that in 3 dimensions? If I change x to -x, y to -y, z to -z, what would the determinant become? It would have 3 diagonal components, each of which is -1. So the answer would be -1. You cannot obtain it by rotation. You can't change a right-handed coordinate system to a left-handed one by rotation. You'd have to flip things over. You need a 4th dimension for that. We don't have one. Okay. So the moral of the story is, first, that a rotation is defined in this fashion properly in any number of dimensions. Second, parity, which is taking r to -r, is a proper transformation in an even number of dimensions, and it's a rotation of some kind. But in an odd number of dimensions, it cannot be obtained by rotations alone. You have to have a reflection somewhere. Okay. So as you can see, very simple geometry leads to very profound consequences. You have to be very, very cautious about the whole thing. I won't prove here that you need an axis of rotation in an odd number of dimensions, but in an even number of dimensions, there is no such thing, not necessary that a rotation has an axis to rotate about. Let me give you an example. In 2 dimensions, you already saw it. We rotated about the origin. Suppose you have 4 dimensions. Call the coordinates x1, x2, x3, x4. You can form 6 different planes. You can form x1, x2 plane, x2, x3 plane, x3, x4 plane, and then x1, x3, x2, x4, and so on. Right? Suppose you rotate in the x1, x2 plane, leaving x3 and x4 unchanged. So 2 of the coordinates are left unchanged, 2 of them are rotated so that there is a linear combination of the 2. Right? It doesn't affect either the 3 axis or the 4 axis. So what do you mean by an axis of rotation? You don't need an axis of rotation at all. But in an odd number of dimensions, it turns out you can always identify an axis of rotation for any rotation. So the moral of the story, when this study finally leads you to the conclusion that even in Euclidean spaces, even in odd dimensional spaces are very different from each other. They have remarkably different properties. For instance, you would have heard of the cross product of 2 vectors. What is meant by the cross product in 2 dimensions? Suppose I have just 2 dimensional vectors. What's meant by the cross product? There is no perpendicular. The space is just 2 dimensional. There is no perpendicular. Right? So if you had in a vector A is A1, A2 and B equal to B1, B2, then the combination you can form is A1 B2 minus A2 B1. That's the only combination you can form which involves both an A and B are really linear in the two, right? If you had a third dimension, then this would be one of the components of the cross product. But you don't have a third dimension. This is a scalar quantity.
It's like the determinant of the matrix.
It is, it's precisely that. Precisely that. It's got the area formed by the parallelogram formed by A and B. But the point I'm making is that the cross product notion, that the cross product of two vectors is again a vector, is valid only in 3 dimensions. In 2 dimensions it becomes a what's called a pseudo scalar. In higher dimensions it becomes a tensor of various ranks, rank 2 less than the vector itself, etc. So again, 3 dimensions has very, very special properties, many of which are responsible for the universe as we know around us. Okay?
What is a tensor?
Now that we know what a vector is, we can define what a tensor is. Let me write the law of what a vector is in this form. Under a rotation, what a vector does, right? Under a rotation, a vector A in any number of dimensions goes to A prime such that each component AI is some rotation matrix AJ. It's a linear combination of the original components of the vector. This is what it is. The summation over J is implied. This is the convention that Date was talking about this morning. So whenever I repeat an index, assume that it is summed over all the allowed values of that index. So this stands for n terms in n dimensions. The rotation matrix is R. Okay. But you can have a quantity like this. I take 2 vectors. Now you are used to the scalar product of 2 vectors, which is dot product, which means A1 with B1, A2 with B2, etc. You can form other combinations. You can form AI with Bj, and if I and j run over, each of them runs from 1 to n, you have n squared quantities, which you can write as an n by n matrix, right? That matrix will transform like this: R I K R J L. So you have a quantity which has 2 rotation matrices in it for each of the indices, and you have a combination which involves 2 indices here, and that's called a tensor of rank 2. So generalizing this, any set of n squared quantities, or in 3 dimensions 9 quantities, which transforms in this form is called a tensor of rank 2. Now you can build up tensors of rank 3, 4, etc., etc. These are called Cartesian tensors. There are other kinds of tensors as well. So, the dimension, the components, number of components in the space. In 2 dimensions it runs over 2 values, in 3 it runs over 3 values, 1, 2, 3, etc. Just labeling the components.
So what is a pseudo scalar? You said that the cross product in a 2 dimension.
Okay. This brings us to the concept of parity. So let me explain what parity is. Let's look at 3-dimensional space so that we are fixed with our physical value. This is called parity. It's called the parity transformation, where you change from R to minus R by reversing all the component signs for the coordinates. Okay. Then you ask, are various laws invariant various quantities? How do they transform under this change? Okay. What happens to this? I take two ordinary vectors A and B in 3 dimensions, components A1, A2, A3, B1, B2, B3. I form the dot product, and now I apply the parity transformation to this. What happens to it? A goes to minus A and B goes to minus B. What does A cross B do? A dot B do? It remains the same. It remains A dot B. That's called a scalar. This is a scalar, right? What happens to this? The momentum P of a particle, by the way, that's equal to the mass times velocity in the most elementary case. What happens to the velocity under parity? So let me call P the parity transformation. What does the velocity do? The velocity is dr over dt. Does dt change? No, only the coordinates are affected. Dr changes, right? So the velocity goes to minus the velocity. So you can form a whole dictionary now. This goes to minus mv. For consistency, therefore, p must go to minus mp minus p. So what does the scale, what does this quantity look like? R dot p, what does it do? Does it change sign or not change sign? It doesn't change sign. R changes sign, P changes sign, this vector doesn't change, this scalar quantity doesn't change sign. It's also a scalar. What about this? This is, by the way, the orbital angular momentum. What does it do? Does it change sign or not change sign? Why do you say that? R changes sign, P changes sign, so R cross P, does it change sign or not change sign? It does not change sign. It does not change sign under rotations, right? So this is called a pseudo vector or an axial vector. Now look at what happens to this. What does that do? That's a scalar quantity, but what does that do under parity? This changes sign, this does not change sign, so the dot product changes sign, but it's a scalar. So it's a pseudo scalar. Okay. So under improper transformations, the pseudo guys have the opposite property to the regular guys. So you have a pseudo scalar, pseudo vector, pseudo tensor, and so on and so forth under improper transformation. You have to ask, is the fundamental law law under parity invariant under parity or not? That's important. What does the electric current do? What does the electric current J do? Does it change sign or not change sign? Now you need a little bit of physics. How do you define the current or current density? Charge crossing some unit area per unit time, whatever it is. Does it change sign under it? So it involves the average velocity of electrons or whatever is conducting, and that changes sign. So J is certainly a normal vector, it changes sign, right? What about the electric field? What about the electric field? Well, the electric field multiplied by the charge is equal to the force, and the force is an ordinary vector. So this guy is an ordinary vector called a polar vector. So E changes sign under parity. Agree? What does this do? What happens if you have a charged particle of velocity v in a magnetic field B? What's the force on the particle? What's the force on a particle of charge q in a magnetic field B? In an electric field E, the force is q times E. But in a magnetic field B, yeah, so that's the formula for the cross product. So what's the actual formula? V cross B. So under a this is part of the Lorentz force. If you also had an electric field, you would have a q times E. But right now we are not interested in the electric force, we are interested in the magnetic field here. This is the force on a charged particle of charge q in a magnetic field B. This applies whether the field is constant in time or constant in space or varying in space and time, we don't care. This is certainly true. V is the velocity of the particle, instantaneous velocity. This is an ordinary vector. It changes sign under parity. V changes sign under parity. This law must be invariant under parity. So what must B do? It cannot change sign. Cannot change sign. So it's not an ordinary vector, it's a pseudo vector. So you can build up a dictionary of physical quantities and how they transform by using one law and then from that following all the way. Are you familiar with the concept of a vector potential? What is this? You know that an electrostatic field E can be written as minus the gradient of a scalar potential phi. Is this familiar to you? That's the formula for the gradient in a special coordinate system. This fellow is an operator that stands for delta over delta x, delta over delta y, delta over delta z, with components Ex, Ey, Ez multiplied by I, J, K, whatever. Under parity, this fellow changes sign. This guy changes sign because r goes to minus r and these are derivatives here. So it's consistent with these two changing sign and this not changing sign. So the scalar potential is a scalar potential, real scalar. It's not a pseudo scalar. The reason for this minus sign is completely a conventional, arbitrary matter of convention. The reason for putting this minus sign is because once you attribute the negative charge to an electron, right, negative, positive charges, etc., then once you put a minus sign here, this phi has the connotation that it's the potential energy of a unit positive test charge in this field as far as the electrostatic field is concerned. Okay? It's the potential energy, electrostatic potential energy. Otherwise, it would be the minus the electrostatic potential energy, which would mean one more minus sign to keep track of. So it's entirely a matter of convention. Okay? And what does Coulomb's law tell you? Very similar to Gauss's law, very similar to the law of gravitation, right? Do you know Gauss's law in electrostatics?
Yes.
What does it say?
That
Flux across some closed surface around a charge is equal to the total charge inside and so on. Why is that happening? What's the reason for this magic? It's like you're walking around a building, the compound wall, which is the bounding surface, measuring the electric flux or something, and you know how many charges are inside the house. So it's exactly like walking around a compound wall and telling me what's inside the house. How is this magic possible? What's the underlying physical reason this is happening?
We are measuring the flux.
Yeah.
Flux is only measured from flux that comes from outside and comes inside. So they are
Yeah, that's fine. But why is this? Why is it applicable? Is it applicable to any force law or only Coulomb's law?
even gravitation.
Yeah, but what's common between those two?
One by R.
So if you got a source of field from this point here, and you have a Gaussian surface like this, Gaussian surface like this, etc. Notice that if I draw a cone of this kind, the area here grows like r squared because the solid angle d omega is common. The area here is r squared d omega, it's r prime squared d omega. So the area is increasing like r squared. And if your intensity of the force that's caused by this charge is decreasing like 1 over r squared, the two cancel each other and become independent of the Gaussian surface. That happens only for the 1 over r squared force. It's entirely because in 3 dimensions, the surface area of a sphere increases like r squared. And it's exactly compensated if the force goes like 1 over r squared. There are other forces. If you had lived in n space dimensions, what would be the equivalent of the inverse square law of force? 1 over, yeah. Exactly. So it would not be the inverse square law of force which would have Gauss's law, but some other force law which would have it. Okay. But the geometrical reason for Gauss's theorem is very clear. It's immediately true from here. Okay. So if I have a point source and it's emitting a spherical wave in all directions, and the intensity here is given to you fixed, how will the intensity drop as you go further out in distance? How is the intensity of this tube light dropping as you come from a point source? A point light source increases, decreases like 1 over r squared. Yeah, exactly, 1 over r squared. Why is it that in an operating theatre in the hospital they have point sources, but if you go to hotel lobbies or corridors and so on, they have tube lights, they have line lighting? Why don't they put the same wattage in terms of point sources? What's the advantage? And if you go to even other hotel lobbies, they go one step further. They don't even put tube lights. They put a big plastic sheet and you get a diffuse, you have a planar source of light. Whereas there is a linear source of light as opposed to a point source of light. How does the intensity drop in a point source of light with distance? 1 over r squared. How does it drop with a linear source? 1 over r. Yeah, the electrostatic field from a long line charge goes like 1 over r, right? Yeah, and if it's planar, it's constant. But the intensity is low. So in a hotel corridor, you want moderate lighting, you don't want a bright light, you're not operating. But you want uniformity. So they choose a linear source. And in a lobby, you want even more pleasant lighting. It doesn't matter if it's reasonably dim, because then you don't know what you're eating. But with the same wattage, they get diffused uniform source. They don't like shadows. So they have a planar source as opposed to a linear source, as opposed to a point source. That's why you use a table lamp for the reading and you use tube lights for lighting the house and so on. Okay. All have practical reasons. And they're all based on very simple principles which you have to look out for all the time.
The intensity of the gravitational field, the intensity of electric field, the intensity of how the light will. Why do all of these have a common one?
Where's the 1 over r squared? Let me give a partial answer here. We believe now in quantum field theory, the conventional belief is that forces are caused by the exchange of physical quanta of particles, of elementary particles, which are massless in general. Okay? But if a massive particle is exchanged, then the potential energy due to this particles exchange is proportional to e to the power minus r over some constant lambda sub c, which I will explain in a minute, divided by r. That's the potential energy. And lambda c is equal to h over mc, where h is Planck's constant and mc is the Compton momentum corresponding to rest mass m of the exchange quantum. In the case of a photon and graviton, the mass is believed to be 0. So this goes to 0, lambda c goes to infinity, and 1 over infinity is 0, which gives you a 1 here, and the potential goes like 1 over r and the force goes like 1 over r squared. But if you exchange massive quanta, then the force gets cut off very rapidly due to this exponential cutoff, and it's a short range force. That's the reason weak and strong interactions, nuclear forces, are extremely short range, because the quanta exchange have masses. Okay. So that in a nutshell is the basic reason, but now you have to put in all the whistles and bells and so on. Okay. Okay. I think there's someone.